So, good morning, everyone, and welcome to our new webinar about using RIIM for smart street lighting networks. First of all, my name is Omar, and I'm the applications engineer at Radiocrafts. It's nice to be speaking to you this lovely morning, which I hope is truly lovely and stays a nice day till the end. I'd like to say hello to everyone, people listening from the US. I guess it's a different time zone, but thank you for joining. And yeah, so today we will speak about using RIIM for smart street lighting networks, and we will present some simulations results. I'm going to speak today for about 30 minutes, the duration of the presentation, and at the end there will be a 10 to 15 minutes Q&A session afterwards. So as you are already doing, please feel free to introduce yourselves in the chat window. And you can also post your questions in the chat window during the webinar while I'm still speaking, and we will try our best to answer them at the end of the webinar in the Q&A session. And as usual, we will post a recorded version of the webinar on our website, and you can check it out after the webinar is over in case you need to revise something. So I will start by first introducing smart street lighting solutions and why they are gaining much attraction in the market these days. Then we will speak about some of their most common challenges in implementing smart street lighting networks. Then the possible RF connectivity options like low power wide area networks, cellular or proprietary, star, topologies, or mesh. Then we will discuss a little bit about RIIM. Then we introduce the simulations results. So, smart street lighting, before it became smart, like the old style street lighting, it was responsible for around 19% or around 1/5 of the electricity usage around the world. And on a city level, street lighting is responsible for up to 50% of a typical city's electricity usage. As you can imagine, that's a lot of energy, a lot of carbon dioxide emissions. But the good news is this is avoidable when switching to smart street lighting solutions, as we will explain very shortly. So the benefits of using smart street lighting solutions are twofold. Firstly, there are the benefits of having a smart network. The common benefits of having smart networks, such as setting automatic lighting and dimming plans, setting the lighting intensity to change in accordance to sunlight, and so on. The second group of benefits revolve around the lighting technology itself being used. Smart street lighting applications use LED lights, which offer significant advantages over conventional lamps, such as better nighttime visibility and less light spillage into unintended areas, and so on. However, as nice as the idea might look, there are some practical challenges that delayed the wide-scale adoption of smart street lighting networks. The challenges are basically divided between the three different aspects of any smart street lighting network. Number one being the RF technology involved to enable the network, and the second being the management center technologies, and lastly is the lighting technology itself. All these aspects must be mature enough to present a stable business case to encourage investors to enter into that field. So if we speak a little bit about the challenges, starting with the first one, the RF technologies. Well, that's since this is your field, so you already know very well the recent advancements in the RF field that has given rise to various novel solutions in the license-free bands. Also, even on the hardware side, the hardware field has led recently to having low-cost hardware being available. So that one is pretty much solved, as you know. The same has happened recently with the management center systems, which have developed a lot and became more available and more secure, especially with the rise now of cloud services with their very customer-friendly data visualization tools and so on. Lastly, technological advancements also encompass the lighting technology, which has seen much progress lately. For example, the most widely used light bulbs in the past were the HID, mercury vapor, and sodium halide bulbs. But then the switch from these technologies to the LED bulbs offered a 52% reduction in energy usage over HID and around 26% reduction over sodium halide bulbs. That's in addition to providing some new features such as reduced glare and better color rendering. Um, Although LED lamps have initially a higher cost, a higher initial cost, but the above mentioned features added to the fact that LED lamps have much longer lifetimes, they make it a very feasible solution for large-scale street lighting systems, and this encourages investors even more. Okay, so now I guess we can address the million-dollar question. What connectivity method or RF technology shall I use in my smart street lighting network? In general, two main categories of low-power wide area networks exist, cellular and proprietary. So with cellular LP-WANs, the most common options are narrowband IoT and LTE category M1, which are both, you can say, variants of LTE. Um, they both share some common drawbacks, such as since they're variants of LTE, so you need to pay a subscription fee, which might sound okay if you have only one device, but since we are speaking about large networks with hundreds or thousands of nodes, so then the fees become a lot. In addition, mobile networks in general can't reach 100% availability, which in street lighting will mean that there will always be unreachable poles, which isn't very practical, to be honest. And another thing that shouldn't be a problem, but now it is a problem with cellular technologies, is that they develop very quickly. Um, so the turnover, the technological turnover, if you say, is very quick. Like maybe 5, 10 years ago, you wouldn't have imagined that 2G networks are being rolled out and being removed from networks, but now they are. So you might install a cellular LP1 in your street lighting network, then you find out that 3, 4, 5 years later, there's a new technology. And the base stations of your cellular provider doesn't support this technology anymore. Then that will be a very big problem. So I guess it's not always nice to have such a very fast-paced tech advancement. With the proprietary LP1s, you have star topologies like LoRa or Sigfox, which are mostly optimized for uplink. So that makes it not a very good fit for control networks, because control networks, they depend mostly on downlink. And something else about star networks is that they always have to be, all nodes have to be in direct contact with the gateway. And that might not be always possible, especially when you're in the streets, because there might be a light pole behind the tree, behind the building. Maybe there is no tree today, tomorrow there is a tree. Maybe there is no building this week or this month, but next month there is a building. So in the street, things tend to change very quickly, and having a very rigid architecture is not maybe very practical. On the other hand, mesh networks offer a good solution to tackle the challenges we just mentioned. They offer a dynamic and versatile network architecture, which serve to mitigate many of the shortcomings of star and satellite architectures. Mesh is generally also easy to implement in street lighting scenarios, as usually there is line of sight or at least limited range between each lamp pole and the other. A next feature of the mesh is that each node can communicate to at least 2 or 3 light poles in each direction. And this is very important in order to create redundancy and the network and avoid, as you call, single points of failure. So since we are Radiocrafts and we are discussing mesh, so of course we will discuss RIIM. Maybe you heard this particular slide before, but very quickly, for those who haven't, RIIM is an industrial grade wireless sensor network with direct IP connectivity. RIIM is based on the IPM module, which can be configured as a border router, a mesh router, or a leaf node. The leaf node usually sits on the edge of the network. It collects sensor data and forwards it to its parent node. It can also be configured as a sleepy node to save battery. Now, the mesh router is basically the same as a leaf node, except for the fact that it can't go to sleep, as it must always be awake to route data of its child nodes to a parent node. Lastly, the border router acts as the root of the network. It has an Ethernet connectivity option, which allows it to forward the network's data to an external server, say a cloud, for example. The new thing, which we haven't discussed before, is TISH. Radiocrafts will be releasing, I think this month, yeah, by the end of this month, we will be releasing TISH in the new RIIM SDK. The basic idea behind TISH is that the nodes, they form a globally synchronized network. The network broadcasts beacons, which contain timing information to let other nodes synchronize and join. So the airtime is divided into continuously repeated set of slots, and a node is only allowed to communicate during its assigned slot. So child nodes have to always correct their clock drift to their parent through timing information in acknowledgement packets. So since a node is not always sending, is not always transmitting, it only transmits in its assigned slot, then it can go to sleep in other times. And this is very important because this enables battery-operated mesh routers, which many customers have been asking for, and we believe it's important in many applications. So with this, you will have sleepy leaf nodes and also even sleepy mesh routers. And another thing is that, of course, it makes the network more resilient to RF interference, make it more reliable, and it enables frequency hopping, which is a requirement for certifications needed to enter the US market. So in short, what will I gain if I use RIIM in my street lighting project? You will have first multicasting, which we will discuss in more detail very soon. You'll have RIIM's support, RIIM's ability to support 28 hops, some features like faulty node detection, supporting UDP packets, which don't require acknowledgements. And of course, RIIM modules support easy. You can also do over-the-air updates and supporting multiple frequency bands. So a little bit about multicasting, because we believe it's a very important feature. So multicasting, why it's important is because it gives the ability to address all lamps or all, in general, all nodes in this application, or lamps, or a group of lamps efficiently and in a close to real-time manner. So how this happens is that in, you say, classic multicasting, border router sends a message and it wants it to reach all the nodes. So as you see in the figure, in step one, the one on the top left, the green node sends it to all its neighbors, which are the two blue on the right and the one blue below it. Step two, the one which was blue before now is green, and it will send to all its neighbors, including the one that it received it from, and here and one new, and then the same, and then the same. So this keeps happening throughout all the network. This is called multicasting via network flooding. It's called the network flooding method. And it's not, it does what it says, it's multicasting, but there can also be a smarter way, which is multicasting for lossy low power networks, or MPL. So with the concept of MPL, control packets which are sent regularly between nodes, these control packets are synchronization packets, which compare how many multicast messages each node has received from a given node. So if one node has received more multicast packets than their neighbor, this missing message is then forwarded several times. This is the reactive forwarding that happens when a multicast message is not spread to all devices. So this method gives a much higher reliability than flooding, and it means that the message can survive longer in the network. But of course, to do this, each node must must have the ability to store a message in case its neighbor didn't get it. Okay, and now for the interesting part. So why do we usually try to simulate scenarios? We often get asked questions like, how many nodes can I maximum use in my network, or how long will the latency be in my network, or how often can my RIIM network send data? Which are basically very smart questions, and knowing their answers is very important, especially during the design phase of the project. But answering them is not that easy, because each of these parameters depend on so many variables. So sometimes weighing all these variables in one human head is just not very possible. So instead of trying to actually set up real life tests for every use case and for every question we get, it's very cost and time efficient to just use simulation software to get the right answers and help our customers. And that's what we started doing here for different street lighting use cases. So we wanted to start small, then we can build bigger and bigger. So we started with a very basic use case. Case number one, it entails having 100 nodes. They are in simulated 4 kilometers straight line street. We set the distance between each light pole to be around 40 meters, with the broadcast or multicast message sent every 4 hours. So every 4 hours, the border router sends a multicast message over the network. And sensor readings from each pole are sent back to the border router every 2 hours. So you have one big downlink, which is multicast every 4 hours, and then from each node, you have sensor reading or status message or whatever you want to do it every 2 hours, uplink to the border router, which we call Unicast here. Assume the maximum range of communication for each pole is 200. Of course, RIIM can reach way more than 200 meters, but we set it to be 200 in this simulation. Because if you set it more, then you will message will be heard in more light poles. So it's an important parameter. So we chose just an average number. And then for the second case, we in addition to the 100 nodes simulated, we added more nodes to make the network reach up to 450. That's what we did, but our next step, what we're looking forward to right now, what we're working on, is to simulate for up to 1,000 nodes. I guess that will also deserve a webinar. So when you simulated the first use case, we got some parameters, some important parameters. We know the network formation time, the latency for multicast, unicast, the number of hops, the topology, and so on. If we start by first the network formation, time for a network with 100 nodes, with all the network formation and rerouting packets being sent, it only took around 6 minutes for the network to be formed, which happens automatically without any configuration or any setting needed from the user himself. That's for the 100 nodes for case one. For case two, we simulated for 400, up to 450 nodes, and we found that the time needed to form that network was still around 6 minutes. So just because it's not linear, if a network of 100 nodes is formed in 6 minutes, doesn't mean that 200 nodes will form in 12 and so on. It doesn't scale up linearly and doesn't even scale up at all in that manner, because when we multiplied the number of nodes by 4, still the number was the same. So we believe that the reason for this is that the network formation time is tied to the longest, is dependent on the longest hop chain. So it will always depend on the logical topology rather than the number of nodes itself. Okay, so what is a logical topology? In the figure you see here, that's the logical topology. It's not physical in the sense that this doesn't describe how the nodes are arranged. So this doesn't mean that that there are nodes here and then a branch and nodes there. So this is not a drawing of the streets in the city. Not at all. The street we simulated is a straight line street, or a straight street, if you might say. But this is rather the logical topology, how nodes are connected to each other and to the border router, and how many hops and who is connected to whom. Because it's not always that all nodes are just cascaded in a chain, one after the other. Sometimes the mesh decides it's smarter to connect, like here, like this chain, and then to the main one, and then this branch and the main one. So we found that the furthest and most remote node in this network is 20 hops away from the border router. In some cases, the best route for a node was to connect to the string in a straight line manner, and in other situations, it was best for a node to form a little mesh at some points with only one of the nodes of that little mesh laying on the main string. So it always depends. So how frequent were we sending packets in that simulation? The simulation was around 24 hours, one day, and around around 500,000 packets were sent. That's if you divide by the time, that's around 6 packets per second. And around, you can say around half of the packets were MAC layer acknowledgements. If you choose, if you randomly pick a node, in that case, when we did it, it was the node number 75, which is around 3 kilometers away from the border router. We found that it sent 1,731 packets in the same amount of time simulation, which is around 50 seconds between each packet. Of course, the closer the node is to the border router, the more packets it will be sending, because it's routing from many branches. So that always depends when you randomly choose a node. It always depends on its position in the hierarchy of the mesh. Okay, how about when the question is asked, like, how much time will it need for my message to reach all my nodes, for my broadcast message to reach the nodes, which is multicast latency. 5 multicast messages were sent from the border router to the nodes. The average time observed for the 5 messages was around 31.4 seconds. For case 2, the average multicast latency was around 27 in average. So you might see that when you multiply the number of nodes by 4, or by even more than 4, the latency actually decreases. Again, it doesn't scale up in that manner. Maybe just the topologies in when you have more nodes, you have more branches, you have more ways for the multicast message from the portal router to reach the node. When you have only 100 nodes, or when you have 450 nodes, when you have more nodes, you have more paths, you have more routes, you have more ways for your message to reach from the border router to the nodes. This might make it reach there in less time. That's why even if you multiply the number of nodes by 4, the latency actually decreases, or at least stays the same, which I guess is, I believe this is one of the best things about mesh, is that it doesn't, it has this intelligence. It's not, doesn't just scale up, and not everything just adds up, and then the more nodes you want to have, then everything just falls down and falls apart. Mesh is smarter than this. And now unicast latency, which is the latency from each node up to the border router. I think the best way to analyze the unicast latency is with this graph. Every 2 hours, all nodes send a status message to the border router, and their latencies are recorded. As you can see on the horizontal x-axis, the further, so on the x-axis, it's the nodes, the node number, and it translates to how far it is. So node number 99 here on the far right is very far from the border router. It's the furthest, and the smaller the number is, the closer the node is to the border router. So that's why you can see that for node, as the nodes, number of nodes increase, the latency increases, because it takes the more hops it takes to reach the border router, the more the latency is. But still, the average latency for the furthest node is less than 1 second, which is pretty impressive for 20 hops. And our next step after these simulations is that now we are working on a very big simulation for a network of 1,000 nodes. I guess that will be very exciting, and we will display these results to you as soon as we have them. I guess still here, my part is over. I will leave you now with Urian, our R&D director, to answer your questions. Urian, you have the mic.
Thank you, Omar, for that presentation. So I would like to go through a couple of questions now. First, we have Harald from Germany asking about these 2 or 3 poles. Of course, we can reach much more than 2 or 3 poles. So the we know that RIIM has in a line of sight area, let's say in a city along a long street, we think it's limited about 1,000 meters. And we also know that the average distance between light poles is, we have used 40 meters. So that means we can actually have quite a big number of light poles we can reach. So this will, of course, these numbers which we put into the simulation affects very much how the network formation will look like. And that's why we chose to have, in a simulation, we used 5 poles. So that means we reach 5 poles in a straight line. So that means 200 meters. And if we put that to 400 meters, we would have a better network, we believe, because with 400 meters, we would have it will be fewer hops, but it will be so it's more a high density network than a widespread network. But these are all parameters that we can now very easily modify, and this is also why we simulate, because we know that if one customer is doing streetlights in a park where it's 20 meters between the nodes, and if another customer is doing highways where it's 60 meters between the poles, that will actually give very much different network topology and results. And yeah, this is kind of the core reason for simulating. I hope that covers your questions, Harald. Yeah, there was some questions about the internet backbone. And of course, this is our RIIM network is IP based. So basically, what you get from the board router is basically a Ethernet connection where we have it acts as a router, as I said. So it has we have a NAT in there with fixed with static NAT address, so you can address each of these 1,000 nodes which the network is designed for directly, and that means you can extend this from Ethernet. You can also, of course, then extend it to Wi-Fi or 4G or any type of IP-based connectivity out to the external world. Also has some private chats here. I won't release names, but we were discussing simulation available for customers. So it is a general topic, so I will cover it here. We will not offer this as a tool to the customers at the moment, simply because it is the tool is quite complex. When we do the simulation, we're actually simulating the real C code that we're running on the nodes. We're putting the same C code and compiling it for these virtual nodes. So we're actually running this on the true C codes that we're using on the nodes. And yeah, it's kind of complex to use, and we of course we don't want to share our source C code with our customers. So it's also a reason why. But we are of course open to doing simulations more or less for customers. If it's something very similar to what we already simulated, it could be very easy to do a quick change and do another simulation for a customer. If a customer needs something completely different, we of course need to look into the business case. Setting up a complete new simulation will take us a couple and doing a completely new simulation might take us 2-3 days. So we have to look into each case to see if it makes sense business-wise for us. But that's any input you have is of course welcome, because we want to make these simulations as close to the real world as we can, and to your cases. Okay. I think that covered all the questions. I don't see any more questions here. So,
sorry, I see quite a few questions here.
Oh yeah, sorry. Now it was. Now I have more questions here. Sorry.
Okay.
Okay. Yeah. So Peter, suppose I have 1,500 lamps. So what we have done so far is that we have dimensioned the network for 1,000, and that's what we're kind of saying. That does not mean that 1,500 lamps is out of the question, but then we need to look carefully into that. The challenge when you extend is, of course, that if you use one board router, all the traffic has to go through that one board router. So it could be an idea to spread it over multiple board routers, simply to spread the traffic. So it's more, today there's a limitation in 1,000. That's something we potentially could look into extending, but it will also depend on the traffic, how much data you want to send, because every node generates some sensor data. Typically, you want to send control data down, and even there are some network or how should I put this, background packets to keep into network control data going in the background, which also increase by the number of nodes. So yeah, what we suggest is basically to keep it below 1,000. how the simulation consider the polite access policies, which is required for 860 in Germany. Well, I guess according to the CE regulation, you either have the polite access mode, which requires both listen before talk and adaptive frequencies. So we do have listen before talk in the system, but we believe that with this, because we are running quite high data rate and each packet is quite short, we believe that we will be within the 1% duty cycle limitation, which is required for Europe. So we do not currently support frequency agility, meaning that we don't move frequency in case it's noisy, which you would require for the polite spectrum access according to the CE and EN 300 220. Hope that answers your question. Redundancy, border router, edge of network. Yeah, that's a question that we get a lot. So currently how that's supported is that the fact that the customers write their easy application inside the module, and there it's possible to have and registered like a backup network, and so you could have two border routers with different PAN ID, maybe different frequencies, and basically handle this through the easy application as it is today. So it's possible to do redundancy. That does not mean that if the border router goes away, it doesn't mean that the network is up and running again in 2 seconds afterwards. It takes some time to kind of reroute the entire network to a new border router, but that's definitely possible. Yeah, so RIIM has two different options that we can run it in. I'm talking about Rob, who now has a question about, he said that I recall the RIIM, it means time synchronization. So will individual poles have awareness of real time? So the RIIM comes in two different flavors. One is the single channel mode and one is the frequency hopping mode. And the frequency hopping mode is a time synchronized frequency hopping. So in that case, they will have a time, a real time awareness, yes, and that is typically, yeah, what is the level of jitter involved? There is some synchronization mechanisms between each node there, so that means I know it's typically like less than 1 millisecond, or maybe it's like 0.5 millisecond the time synchronization between the nodes to make sure that they hit these time windows. Each time window they operate in is 40 millisecond long, so that is kind of the level. I don't have an exact number, but it's in that ballpark. The simulations we have done and presented today is all based on single channels, so these are not based on the simulation we have shown today are not based on time synchronization and fish. Yeah, a couple of more questions here. We're a bit over time, but I will try to cover the two last one as well. Duty cycle 1% as a function of number of nodes. Yeah, that is for us. It's a complex question from Peter. If you consider that we're using multicast to send control packets, that means that the border router will then only send his 3 or 4. He will send his multicast packets. Maybe he has 2 repetition of it, but he will just send those 2 packets and then he's complete. And all the other nodes, when they get this multicast packet, we only send it 1 or 2 times. So and that is something like being on transmit for something like 20 milliseconds. And of course, it depends on how often you send this message. We don't expect people to send multicast message every minute because to all nodes. So it doesn't scale with number of nodes on that respect. How it scales and also the uplinks sensor data up is of course there will be it will be scaled. It means that if you have some nodes which are closer to the border router and you have a lot of nodes which are further away, all these packets has to go through these nodes which are closer to the border router. So that is a matter of statistical analysis, how your network looks like. So again, if you have a wider network where you can spread it over more nodes close to the border router, it will help. But that parameters do scale with the number of nodes. So, and also the question is, how often do you send sensor data? We have some which says they just send the status message every day from each node, each light bulb, meaning that the status of the lamp and some other statistics calculated over the 24 hours, while other are thinking of sending sensor data every 5 seconds. And obviously, if you're looking at these high advanced systems sending sensor data every 5 minutes, then you could get into some issues. Also, the network traffic that is in the background is also scaled a bit depending on the number of nodes. So, yeah, there is a calculation there. We can take out these duty cycle numbers from our simulators, but we haven't done that yet. So that's one of the interesting things we can do. So if you use multiple border routers, each router will start their own separate network. Or is there a way to do multiple border routers in the same network? At the moment, yeah, there will be separate networks as a redundancy. We are looking into these multiple border routers in the same network. It's on our roadmap, but I don't have an exact date on that yet. So the questions keep popping in here. So I do apologize for going over time here. Yeah, the EC tool is basically the EC that you mentioned is basically the customer can make his own C code describing the operation of the node and download that into our module. So that means he can set up how to handle the incoming multicast packets. He can set up how to handle he can set up a timer every 2 hours to send some status up as we have used in a simulation. He can also do a lot of logic. He can read a light sensor and do some individual control. So there's a lot of, basically it allows customers to write their own application inside the module and define the behavior of that exact module. So that means he can get a multicast packet, so he can then take it and rewrite it to some DALI protocol or D4I protocol to control the lamp directly from that. So that's all the intelligence that you put into the EC application. We don't have a plan to do a Mac version, so currently we do support Windows and Linux as the development tool. So that's what we have on our plan as of today. Link budget of the application is, well, the link budget of one link is 14 dBm mentioned 110, so that's 124 dB in one hop. We have 14 dBm output, and the sensitivity at 50 kilobit that we run with RIIM is minus 110. And of course, Harald, as we both know, it's the background noise in a city will limit this in a real urban environment, as it will do with any sub-1 GHz network in a city, because there's a lot of background noise. So, but the 1,000-meter range that we've seen is with that background noise. If you put this out on some lighting on a mountaintops, then you probably reach like 5 kilometers. But we really don't use that. I don't like to use those numbers because they don't really give a useful data for the customer. That's just for marketing to have 5 kilometers. So we do like to operate with, take this background noise into consideration, and then we're limited to like 1,000-meter line of sight in a city. Okay, I think that covers it. So thank you for a lot of very good questions, and I think I covered most of them. If you have more questions, you're free to email us after this. I'm sure you can contact us, and we would like to wish everybody a good day and stay healthy. I guess most of you are at home due to this the corona situation. So please stay safe and stay healthy, and we will come back with a new webinar in a month's time or so. So thank you very much.